Hi, good morning. I'm Sachin Kadian, Servo Fellow at University of Alberta and PhD scholar at IIT Roorkee. Would like to thank the organizing committee of IEEE Sensor for providing an opportunity to present my work focused on the ultra-sensitive fluorescent paper-based acidic gas sensing platform carried out at University of Alberta in collaboration with IIT Roorkee. So first, I will quickly go through the uh, uh, outline of my presentation. In this short talk, I will briefly discuss the need of acidic gas sensor. Before moving on to the developed sensing probe, I will quickly discuss about the conventional fluorescent probe responsive to acidic gases. Then I will introduce you with the synthesis and characterization of red emissive sulfur, followed by the development of fluorescent paper-based sensing. And before concluding, I will discuss its application part. So, in the past few years, with the advancement of Internet of Things technology, acidic gas sensing has been integrated in industrial smart sensors across the globe. So these hazardous acidic gases are commonly generated from absorbing tower of semiconductor plants, incineration of plants, and burning of halogenated polymers. Further, an accidental exposure to high concentration of these acidic gases can significantly affect the eyes, respiratory system, mucous membrane, and skin of industrial workers dealing with the gaseous products. Therefore, the selective and sensitive detection of highly corrosive, toxic, and hazardous acidic fumes has attracted significant interest from the scientific community to monitor the air quality in open as well as closed environment and to ensure the safety of industrial workers. So, the conventional fluorescent sensing probe have already used organic dyes, that is porphyrin. And if we see the performance of an optical gas sensing probe is highly dependent on the diffusion of annihilate fumes into the sensing platform. Therefore, due to porosity and good accessibility of gaseous annihilate in the sensing material, micro and nanostructures such as nanoporous fibers, micro nanoporous films, and honeycomb film have widely been used as a substrate matrix for the incorporation of this organic dye and development of this gas sensor. So these days, to replace these electrospin nanofibers, nanoporous films, and honeycomb structure, fluorescent paper-based gas sensors have gained significant attention because of their extreme low cost, desirable porosity, biodegradability, and versatility. Therefore, in this study, we have replaced the traditionally used porphyrin with our synthesized red emissive sulfur. In this, the aggregation-induced red emissive sulfur was synthesized using two-step oxidation process, as shown in the figure. Initially, an estimated amount of bulk sulfur and sodium sulfide was mixed into water and dissolved for 1 hour, and the after 1 hour, the obtained pale yellow color solution confirmed the formation of sodium polysulfide. Next, for the first step of oxidation through molecular oxygen present in the water, the yellow color solution was further allowed to steer for 70 degree and for 12 hours, and the color was changed to transparent solution. And this solution was then freeze dried for the next step of oxidation. For second step of oxidation, the freeze dried sample was exposed to air, and upon exposure to air, the temperature of obtained a powder sample sharply increased from room temperature to around 470 or 480 degree, which was monitored by infrared thermometer. And within few seconds, the color changed to brown. And could be like ascribed to the oxidation of elemental sulfur or polysulfides. After a few minutes, the brown color powder changed into the light yellow and exhibited intense red color fluorescence under the UV lamp. Before using these red emissive sulfur paper as a acidic gas sensor, a few necessary criteria were carried out to confirm the successful synthesis of red emissive sulfur. So first we did UVVS absorption spectroscopy and found that the absorption band centered at 370 degree, 370 nanometer, and a shoulder at 420 nanometer in the UV-VS absorption spectra of red-emitted sulfur indicate the presence of S8 and S4 phase of sulfur. That is, if we can say that is elemental sulfur. And next, the XRD pattern of red emission sulfur shows six prominent peaks at 2 theta 23.7, then 28.8, 32 point, and 34.48 and 59. Similar to the signature peaks of host component sodium thiosulfate Na2SO3 of red emission sulfur. The presence of Na2SO3 characteristic peak in the XRD pattern also confirms the successful completion of step 2 oxidation of Na2SO3 due to sharp increase in the temperature. Additional XRD peaks at 25.4, 25.7, and 27.4 and 45.3 are attributed to the incidence of unreacted Na2S present together with the elemental sulfur. Next, the for the more characterization and for insight into the structure, FTIR and Raman spectra were performed. The peaks located at 495, then 630 and 978 and 1140 uh, uh, around these wave numbers. The FTI spectra of red emission sulfur are analogous to the characteristic peak of Na2SO3 and thus confirms the presence of the host component in the FTI spectra as well. Further, the Raman spectra of S in the red emission sulfur was acquired and shown in the figure. The strong doublet peak around 985 and around 950 or 48 and signify the characteristic peak of Na2S and Na2SO3, which is also in good agreement with FTIR and XRD of our synthesized red emission sulfur, and also in good agreement with the previous reports. The Raman peak located at 635 and 145 or around 495 are ascribed to the S4 and S6 phase of elemental sulfur. So these results enable us to conclude that the elemental sulfur is embedded into the framework of Na2SO3 and thus exhibits aggregation-induced red emission in the solid phase. After the confirmation of successful synthesis of red emission sulfur, we used this red emission sulfur to infuse into a standard filter paper for the preparation of fluorescence sensing probe. So we used a 2 by 2 centimeter filter paper and infused the red emission sulfur, as you can see. And then the colorimetric response of HW sensing probe against acidic vapor was analyzed using 365 nanometer UV lamp. So it was observed that the surface of the sensing probe quickly responded to both acidic vapors, giving rise to color variation, as you can see. And the apparent change in color of fluorescent paper with varying exposure time from 0 to 15 seconds for HCl and for 0 to 50 seconds for HNO3 was observed. It can be visualized from the figure that the HCl reacts more quickly as compared to HNO3 and eventually turned the red filter paper into the black one. So this visible change in color of sensing probe allow us to conclude that this type of fluorescent paper can be used for an efficient acidic gas sensing platform. So conclusively, we have synthesized red emissive sulfur using two-step oxidation process, and then we incorporated this into the Saturn filter paper, and then we we, uh, we can also conclude that as this process requires no virtual simulation and testing and processing, so this provide us the with very simplicity and cost-effective sensors. Further, numerous fluorescent sensing probe can easily be fabricated even from 1 ml of stock solution. So ultimately, we would like to conclude that this technology can find a real-time application in the chemical industry for regular acidic gas monitoring. And here we would like to acknowledge the direct and indirect support from the Future Energy Systems, NSERC, and NRCC, And I would like to thank Department of Science and Technology for facilitating with Sir Bovide Fellowship. And these are some references which are similar to like this work. And next, thank you so much for your patience and welcome to any query if you have. And thank you. Thank you.